This question states, determine the shear stress tau xz at location A, which is along the most y positive line on the surface of the loaded cylinder. Tap is in the positive x direction and P is in the negative z direction. If sigma ultimate equals 100 megapascals, do we expect failure from the criterion of maximum normal stress? Well, there are a couple of things to note. One of which is that we have our variables T app and P for the loads being applied to the system, which means that we won't be able to come up with a definitive answer if we have uh, met or exceeded the criterion of maximum normal stress with a definitive number. Because depending on what P and T app are, we won't be able to figure out, or we would be able to be below the limit or above the limit. Nonetheless, this problem will allow us to kind of present how to do the work, and if you're in the class, you'll have the opportunity to plug in actual numbers and be able to figure out whether or not we would expect failure from the criterion of maximum normal stress. This problem also is a flashback to question number 3 from session 16. So if you would like to go back and let's see, so question number 3 from session 16 has this same configuration with the P and the T app and the cylinder. But let's go ahead and recall what the state of stress at location A might be. And to do that, we can first go ahead and redraw our little cylinder like we have here. And let's just say that this element is up at the top. That's element A. Yes, it doesn't look very beautiful. And we have that X is in this direction, and Y is coming out of the surface. But of relevance here, we also have the Z direction coming out to the left, right? So Z would essentially be this direction over here. And how do we know that? Well, we typically use right-handed coordinate systems. So X cross Y using the right-hand rule, that sends us in the negative P direction. Also, if we look at the wording in the problem, we see that P is in the negative Z direction in the instructions. So we're completely in line with what we have there. So we have now this T app being applied, okay? And let's just think about what that means. That means if I look at the deformation, if I had a line that was coming straight across, right, it's now kind of been twisted at an angle, right, that I'm going to have deformation that's going to be, if I'm looking at this face counterclockwise, right? Or positive x, if you will, which is in the same direction as T app. So we can kind of get an idea that the theta stress, at least from T app, if I draw the stress arrows, it's going to be taking that side of the element. What's this side? This side right here, and moving it kind of to the lefterly direction or counterclockwise direction. And on the other side, it's going to be opposite. I really only need, as you may recall from our time together, we really only need one arrow on one of the sides to be able to draw all the shear stresses, right? So I don't even have to know that it's that direction. Once I have one, I know that I've got to have another pointing to that corner, and then I have these over here that are pointing to each other here. And that way, the element is in equilibrium with respect to the shear stresses that we're placing on it. So if we redraw this element now. So how should we redraw it? Well, let's draw it so that it's a square. And let's say that Z is going to come out of the top. Okay, now this is not a stress. This is just a coordinate system. And let's say that x is coming out the left side, right? That's another coordinate system. So here we now have our shear stress, like this. And look, this is if I just look at this arrow right here, this is on the positive x face in this one right here is on the positive x face in the z direction. So I can say that this is describing a tau xz, positive x face, positive z direction. Okay, and that's what TAP is doing. Now, what is happening with let's say that let's use a different color. We can use green here. So that we have this P that's going across at the outer face. Okay, I mean it's pointed here, but we can say it's really there. So what's happening with the shear stress, okay, because that's what we're interested in, tau xz, due to this P? Well, in this circumstance, what we've got is essentially a bunch of shear stresses, okay, all right, that are going to be coming across, okay, like that. Why? Because this would be the neutral axis, okay, along here with that transverse load P, okay? And so you could think of all these little, if I draw a bunch of little boxes here, okay, that is going to be, those would be having maybe traction vectors on them, or they would be having little shear stresses acting on them along that surface, and that's going to continue along that cylinder, right? So everywhere I look, okay, I'm going to have going down across that longitudinal axis that same set of transverse shear stresses. And this is under kind of the treatment of beams that we've discussed. So if you're not super familiar with the transverse shear stresses, you can look at the session that we have on transverse shear stress in beams. Okay, so what's actually happening on that face is P is contributing a shear stress that is going to be going the opposite direction of what we've drawn here. So there's going to be essentially, so remember this is X and this is Z, right? So that means that this element is rotated 90 degrees from what we see here. There's actually a contribution, if you look here, right? It's going this direction, whereas TF was going this direction. That's going to be going the opposite direction, okay? So this is going to be something like this, okay? So this, we could say, this is going to be the T due to the tau, sorry, due to P, okay? And it's still acting on this XZ plane, okay? It's still acting on this XZ plane, and we're about to figure out what its magnitude is. So, since we're on transverse shear stress, let's talk about what the magnitude of it will be. So for the tau p, which isn't still acting on the xz plane, so I could write, if I like, I can say tau xz p, okay, and maybe I'll change that here to tau xz p, okay, is going to be minus, because look, it's acting on the x face, that is the green arrow, but in the minus z direction. So I'm going to say minus, and what is this value? Well, since it's on the neutral axis, that value is the maximum transverse shear stress. So I don't have to do, yes, I could do like the VQ over IT bit, but really, since this is a circular cross section, it's a cylinder, we can say it's minus 4/3 average shear stress, okay, tau av. So what is the tau av? Well, that's going to be P divided by the cross-sectional area. So that's going to be pi c squared. Okay? So we've got this contribution from P. Let's maybe write it out. Tau xzp is equal to minus 4p over 3 pi c squared. Now, what about the other stress the other shear stress due to Tap? Okay, so we have Tap here. Well, that's going to be what we call in New Jersey, we reference our friends at TCNJ, um, or just the torque times c, the radius divided by the polar moment of area j. Okay, so the tau xz, and now maybe we'll say this is due to the tau xz due to T app. Okay, we can say that that is going to be our T app. Right now, this is not a beam. Before we talked about beams in class, we talked about rods and shafts. So this is in the category of the twisting of a shaft or rod. Okay, so T app C over J, and J is equal to pi over 2 C to the fourth. Okay, I is equal to pi over 4 times C to the fourth. J is equal to pi over 2 C to the fourth. And both of those equations would be for a circular cross section. So we can then therefore write that the total, which color should we use? I don't know. We can go back. We'll say that the tau xz total, or combined, whatever you want to put, is going to be the, let's see, we have pi over 2, so we can get 2 T app C, and actually that's going to knock out because we're going to have a c to the fourth in the denominator over pi c cubed. And then we have the contribution from the transverse shear stress. That's going to be minus 4p over 3 pi c squared. All right? And we can see that these are going to have the same units. We have length cubed, but we have Newton meters, or force times length in the numerator. And over here we have force, and then we have length squared in the denominator. So units all check, and we can calculate these values. So the question is, how do we determine if the maximum normal stress that's possible from this state of stress is going to lead to failure using the maximum normal stress criterion? And for that, what we can think about is Mohr circle. Now, before we do Mohr circle, we should probably just think a little bit about what the state of stress in totality is. We said, okay, determine the shear stress tau xz at this location. But are there any normal stresses? Are there any bending stresses that we have to be concerned about here that maybe we didn't account for? Are there normal stresses or axial stresses that are coming out of this system? Or do we have the case of pure shear, where we have nothing but shear stresses around this element? And so if we come back here, we see, oh, well, P is like I have a load at the end of a cantilever beam. So there should be some bending stresses, and there are bending stresses, but A is on the neutral axis for that applied moment, which would be about the y-axis, right? You think, oh, I'm doing this, but yes, I'm on the neutral axis here, or the longitudinal axis, this dashed line with the longitudinal axis. If I come across, that's the neutral axis. So if y equals 0, right, where you're at a location on the neutral axis, then the bending stress is going to be 0. So there's no bending stress due to P. And we've got the transverse shear stress due to P. So that's it from P. T-app, well, that's a pure twist. That's torsion. That's pure shear. Just looking at it, this T-app is not going to be contributing to any normal stresses to state A or along this beam. So in fact, we have described not just, the state of shear stress, but we've determined the entire state of stress at this location A. And so that means that the other stresses, sigma x, sigma y, sigma z, all equal to 0. Tau xy, tau yz, also equal to 0. So I guess maybe we can, I don't mind writing that out, but we can just say that sigma x equals sigma y equals sigma z equals 0. And we can also say that use a different color, that the tau xy equals the tau yz, and that is also equal to 0. Okay, so this is the only game in town, as the cliche might be. Okay, so that means when you calculate this out, you're going to get some number, right? So let's just call it tau xz. All right, that's the number. So what does it look like on Moore's circle? Let's use this. Well, here's Moore's circle. Here's tau. Here's sigma. This is a state of pure shear. So we're going to be like this, okay? I mean, it should be symmetric there. And we can say that this is tau x z. The one at the top here, that's minus tau xz. So Moore's circle for this system looks like that, okay? So the question then is, where are the goalposts, are they here? Okay, for sigma ultimate, right? Is this sigma ultimate here? Or is sigma ultimate somewhere out here? Okay, that's the question. And if the Moore circle is within, if the Moore circle is within these goalposts, then we're not going to have failure. All right, so let's put this together in a little bit more concrete fashion. In that, we'll say that the sigma 1, and we'll call this sigma 2, right? Sigma 1, what is sigma 1 equal to? Well, sigma 1 is just equal to tau x z, right? Because this is the radius, okay? And the radius is going to be that same distance there as well. And we are concerned about, the question is, okay, is sigma 1 uh, less than sigma ultimate, all right, which in this case was 100 megapascals, okay? And if it is, so we can, maybe we'll change it, not just is, but if sigma 1 is less, then no failure, okay, due to uh, maximum normal stress theory, okay? And this would potentially be applicable to a brittle material. If sigma 1, and also we could say the absolute value of sigma 2 because it's pure shear. If the absolute value of sigma 2 is greater than this sigma ultimate, this ultimate tensile strength, then or if sigma 2 is less than it, all right, then the absolute value of that, then also same deal, because sigma 2 is going to be equal to minus sigma 1, and I guess we can put that out there too. Sigma 2 is equal to minus sigma 1. Now, what if we wanted to plot this on our newly minted sigma 1, sigma 2 plots? All right, so let's say that this is sigma 1. Let's say that this is sigma 2. Okay. You remember that for maximum normal stress theory, you have to be in the box to not have failure. So the box looks something like this. And this point right here is sigma ultimate, sigma ultimate. This point right here is sigma ultimate minus sigma ultimate. This right here is minus sigma ultimate minus sigma ultimate. And this right here is minus sigma ultimate, sigma ultimate. All right. So where do we fall in this case? Well, assuming that, and typically the torsional shear stresses are going to be higher than the transverse shear stress, just because transverse shear stress is typically low. Often you'll see that the transverse shear stress components for bending are in the hundreds of kilopascals, whereas the transverse shear stress, or the torsional shear stresses that we talk about, are often much higher than hundreds of kilopascals, tens, hundreds of megapascals. So assuming this is positive, okay, and then we said that sigma 2 is equal to minus sigma 1, that means that for our problem, which quadrant are we going to be in? We're going to be in this quadrant right here, right? And I guess I can extend it, right? I don't know I'm if I'm inside the box or if I'm outside the box. But if I'm outside the box, right, then I'm going to have failure. And notice that the same rule applies, right? If sigma 1 is less than sigma ultimate, right? So that means, what do I essentially have? Every single point. It's not even that this is the quadrant, right? I can even go further and say that uh, every single point that I'm interested in is on this line. Why? Because this is line with slope -1, where I can say that I have sigma 2 equal to minus sigma 1, right? So, and that's what I said I had in the case of pure shear. So this is called this line, and if you extend it, it doesn't really go. Well, I guess if for some reason this was a very low value and had this, but this line is called a shear line, okay, or pure shear. Sorry, pure shear line, okay, and that's because in pure shear, the sigma 2 is equal to minus sigma 1, and vice versa. Sigma 1 is equal to minus sigma 2. Anyway, so what you're going to be looking at is to see, okay, you're on this line, and are you inside the box? All right, and if you're inside the box, then you won't have failure. Well, I hope this video has been a little bit helpful. It went a little bit long, and some of you are probably like, I got the answer already. Why you keep talking? Nonetheless, for those who are kind of more interested in you being able to use the sigma 1 and the sigma 1, sigma 2 plots, mission Moore circle, which is part of what we're discussing in session 22, I think the extra information might be helpful. Thank you.